Hello, welcome back. So, we are looking for a way to relate angular kinematics to linear kinematics of things, points on the bodies. And we will see here that relative motion is an extremely useful approach to tackle this problem. As a dummy example, I have a randomly shaped body. It is undergoing general plane motion. And for simplicity, let's pretend we know motion of one point. Motion of A, for instance, a random point on the body. And we know the rotational motion of the entire body. And our goal is to find motion of B, or kinematics of B. It is a very general setting. You can mix and match different information. For instance, you can, the problem you're dealing with, you may know motion of A and motion of B. You want to find angular motion or any combination of them. You know two, you want to find the other one. And yeah, the question is how. So in general, we want to find these in a given frame, like let's call it XY frame. XY frame. And you have seen before that we could use something called relative motion. So we have this X prime, Y prime frame. And we could try to relate motion of B to motion of A and relative motion of B with respect to A. So let's see how that works. If I want to translate these known to mathematics, knowing motion of A means I know R of A and possibly all its derivatives, velocity and acceleration. And my goal is to find R of B and all its derivatives. And we have seen before that I can relate these together using this vector triangle. So R of B is, let me write it as position. Where do I write it? Yeah. Position. I can write R of B equals R of A plus R of B relative to A. And this is what observer that sits on A, observer sitting on A measures, or sitting on A and moving with the body. So that's that. That is position. Position is easy, always. What about velocities? This one remains simple, but needs a little bit of reasoning. We can write again, we have seen this before, V of B equals V of A plus V of B relative to A. This is what we are looking for. This is what we know. What about V of B relative to A? And here is what the strength of this relative motion analysis shows up. Remember, we are dealing with rigid bodies. Rigid body means the distance of any 2 points remain fixed. In other words, distance of B relative to A is always remains the same. And as the body moves around, notice what observer A sees. Because the distance is fixed, the only thing A can observe is that B is rotating about point A. This is what observer A sees. Always a line sticking out a certain distance, and the only thing that can possibly happen is that this line in the field of view of A rotates. So, importantly, this is star. V of B relative to A is a pure rotation velocity. And we have studied this before when we were dealing with pure rotation. We could very easily calculate this using the known information about the rotation of the body. Oops, don't go. And here V of B relative to A, because it's a rotational velocity, remember we can write it omega cross R of this position vector, which in this case is R of B relative to A. So putting everything together, let me box this because I'm going to box the next one. V of B is V of A plus omega cross R of B relative to A. And here you see why the vector notation that we introduced in the last section is extremely useful. Let me think. Was there anything else I want to say about velocity before moving to acceleration? Oh yeah, one thing. So this is the vector notation. I'm going to mess up my figure, but I'll remove it later. This vector notation is what I recommend. It is foolproof. It is a little possibly longer to calculate, but it doesn't fail you ever. But we are dealing with, and this works in 3D too. Vector notation always works 2D, 3D, 4th, 5th, any D you want. But if you want, you're more comfortable, because we're dealing with planar motion, all the velocity vectors will remain inside the plane, and all the angular velocity vectors will be perpendicular to the plane. So you can simplify your own calculations. You can consider a direction of rotation within the plane as positive. And if that is your direction, you can know that the velocity vector, this relative velocity, is always going to be perpendicular to the R. So this is V of B relative to A. Perpendicular to the position vector or relative position vector. And with simple geometry, you can, let me write it here. Where do I write it? Here. Magnitude of B is R omega, or let me write it this way, R of B relative to A times omega. And its direction perpendicular to R of B relative to A. And you can, knowing the angle of R, you can find the angle of V and then do your own 2D calculations using the components, for instance. That works, but it is clunkier. Sometimes easier, sometimes a lot more difficult to manage all different terms and directions. So I don't strictly recommend it. Depends on the problem. But I prefer the vector notation. Always works. Okay, that is what I wanted to say about velocity. Let me clean up. Oh, I cannot clean the middle right angle thing. It's there forever. So that is R, that is V. Next stop is acceleration. And identical reasoning, point B in the field of view of A rotates or has a pure rotation. So my acceleration equation, that is A of B equals A of A plus A of B relative to A, this one is going to be a pure rotational acceleration. And I can write these as A of A plus, I had two terms for acceleration, R of B relative to A. No, alpha. Alpha cross R of B relative to A minus omega squared scalar times vector of position. And if you want to write it, A of B equals A of A plus alpha cross R of B relative to A minus omega squared R of B relative to A. And this is the acceleration. Notice that, or remember that, we had two components for acceleration. One was the centripetal one, that is omega cross omega squared times R. And we had I just realized my velocity vector was the opposite, the one I had drawn, but that's fine. So I have acceleration, centripetal acceleration, and the kind of tangential or transverse acceleration, that is alpha cross R. So we have these two, add those to the acceleration of the observer itself, that is A of A. Let me delete these. And that gives you acceleration of B. So really simple equation, simple concept, but extremely useful when we are dealing with complex motion of potentially multiple rigid bodies connected to each other. We can hop from one body to another, relate motion of one point to the angular velocity, to the angular motion of the body, find it, go to the next, and so on. So it is very useful. A couple of remarks before I forget. The most important one is that this x prime y prime frame only translates. Let me write it with better handwriting. This is extremely important because if the frame itself rotates, that rotation creates these kind of hallucinatory velocities and acceleration as observer A observes B, and those need to be taken into account. This is something we will study in the final section of this chapter, relative motion analysis using rotating frames. But for now, remember that it is the frame translates. X prime always remains parallel to x, y prime always remains parallel to y. It doesn't, this frame, x prime, y prime, does not rotate with the body. So that's one thing. The other thing is you need to be careful when you have mechanisms, like you have one link here and one link there. If you have a pin connected mechanism, and this one turns. Let's call this A, B, and C. In pin connected bodies, V of B, doesn't matter whether you calculate it looking at body 1 or body 2, V of B and same A of B are shared between the two bodies because, well, they are pin connected. They are the same point moving with the two bodies. But that is not always the case when you have different kinds of mechanisms. Be careful that this may not work. So the formulation that we have is particularly well suited for these kinds of systems. So that is one remark. And final remark is 2 points having the same velocities does not necessarily mean having the same accelerations. A good example are in gears or where is it? When you have 2 gears or mechanisms, this is one wheel turns this way, this is another wheel turns that way. So this point A, the velocity V of A is shared, is the same, because these two wheels, well, turn each other without there is a slipping between them. But notice that acceleration of A on the first body is not necessarily equal to acceleration of A on the second body. So let's call this 2, let's call this 1. The reason is that point A on body 1 goes around this circle. Point A on body 2 goes around this other circle. So you have these centripetal accelerations that are actually in the opposite direction, or they have different magnitudes even. And note that V being equal does not necessarily mean accelerations being equal. Sometimes you need to take those into account. Okay, that was a busy slide and busy, not a slide, board, frame, pictures, page. And it took longer, but that is all I wanted to say about relative motion analysis. I close this section here. Let me just double check if there was anything else I wanted to say. No, I'm close to perfect. I'm so humble that I don't claim I'm perfect. But anyways, so this is all I wanted to say. We have just two concepts left out of this chapter. We will study those in the next sets of videos. So I'll see you then.